properties of the elements. And again, in this one, I would have a periodic table handy. So first thing we're going to do is talk about the periodic table. In 1869, both a German Julius Mayer and Russian Mendeleev Dmitri had similar arrangements, but Mendeleev got credit for setting up the periodic table because, unlike Mayer, he predicted the missing elements on the periodic table. And if you ever go to Russia, there's a museum, etc. It actually sounds pretty cool. So when we talk about the periodic table, remember that Mendeleev was the one who set it up. Now, it's arranged by periods or rows are the horizontal lines, families or groups are the vertical lines, and then you're going to have your zigzag line as it goes through. Now, the periodic table I'm using, I did not realize did not have a zigzag line, but you can look at it and we'll remember that metals are to the left of it, nonmetals are to the right, and metalloids or semi-metals are on it. So when we talk about the periodic table in general, what we're talking about is the groups. Now, remember we said that these are the s and the p orbitals filling, this is part of the main group or representative, as is this group over here. So these are main group or representative elements. And these basically are the S's elements and the P's. The transition, and like you can see that, let me go to a darker. Transition elements are in the middle. They happen to be metals. These are the inner transition. We've all seen this before. And also known as the lanthanide and actinide series. So when we talk about the periodic table and the trends, we're pretty much talking about the trends associated with the main groups. The inner transition have their own trends, and the transition metals tend to do their own wonky thing. So remember, if we look at our zigzag line, we have metals to the left of it and non-metals to the right of it. If it's on the zigzag line, it's a metalloid. If you'll remember, these are your alkali metals or alkalis, alkaline earths, okay, remember we said this was 1 plus and this is 2 plus when we look at ions, so it's kind of combined. The next group, and I'm going to go from the other end, these are noble gases, or we also refer to them as the inert gases. And they're inert or noble gases because they have complete shells, they don't want to react. The group right next door, which starts with fluorine in its family, are the halogens, and the chalcogens are the oxygen in its family. Now, we've been through those before, so they're kind of back. So let's talk about trends. First trend we're going to talk about is the radii. And when we talk about the radii, we're talking about an atomic radii. And if it's a metallic compound, it's the difference between the two nuclei divided in half. So, for example, if this is 2, then this distance here, here would be 1. Okay? If it's a covalent radii, then it will be a shared bond. And again, you're going to find the distance between the two nuclei and divide it by 2. So this is a different text, but it's easy to see that we're going to increase. And here's the trends. Here's the rule with trends. You either need to pick that you're always going to do increasing or that you're always going to do decreasing, because if you go back and forth, it kind of blows your mind. So I tend to usually go with increasing. So what's going to happen is what happens in a row is as we start adding in electrons, we're just pulling them in tighter so it gets smaller. But with each layer, we're going to get bigger as we go. Think of layers of an onion or nesting dolls. So we're going to increase your radii as you go to the left of the periodic table and down. So basically, the biggest ones will be down here in this corner. Okay? This is the figure they give you in your text, and this just doesn't work for me. You can kind of see that down here we're increasing this way and this way, but it blows my mind, so I can't do that one. So using only a periodic table, the question is list these atoms in order of increasing or decreasing size. Now here's the trick. We're actually looking for decreasing size. I could have asked for increasing size. The other thing is you've got to know where they fall in the periodic table. And so the simplest thing to do is to put them in order. So I'm going to start with bromine. I know bromine is over here. Chlorine sits directly above bromine. Germanium is in the same row as bromine, but over to the left. Potassium is in the same row, but way over to the left. And again, we're ignoring the transition metals. So we did those two and that one, so now we're left with sulfur. Sulfur is sitting right next to chlorine. So we know that we're going to increase going this direction. So when we want to put them in decreasing size, we need largest to smallest. So our largest one is going to be potassium, germanium, and bromine, and then sulfur and chlorine. So if you're given a multiple choice, if you start with looking at the two that are the extreme, that you know are the extreme, then you'll go accordingly. Now, somebody may say, but chlorine is the same row as bromine. Yeah, but there's a bigger jump as you go down a row. Okay? So here's the same thing. Here we're using barium. Barium is down here. Boron is way up here. Magnesium is one down from boron. One row down from boron, but over to the left. Potassium is below boron, above barium. I may not have given myself enough room. And there's sodium right next to magnesium. And they want increasing, so we're going to do small to large. That means that the smallest one is boron, which is really way over here, and the largest one is down there at barium. So then we're going to go backwards, so then it's potassium. Remember, sodium is going to be larger than magnesium. Okay? So, again, if you look for your extremes first, that'll allow you to eliminate everything else. However, be aware that if I had asked for decreasing, then it would be this, but reversed. So that's often a way to get around a multiple choice question is watch out for whether it says increasing or decreasing. Because you get in a test situation and you're like, what? So be careful. All right, so the next trend, we took care of the atomic radii. So now let's talk about ionic radii. Now the size are going to increase as you go down a family. It's a given because remember, it just keeps getting bigger layers of an onion as you go down. But the size is going to vary in a row with respect to, that's what that means, with respect to a zigzag line. So the way what happens is on the left, the ions become smaller than the atom because metals, which are to the left, tend to form cations. Well, remember, cations are when they lose electrons. To the right, they tend to become larger than the atom because these are nonmetals and they tend to form anions, which means they gain electrons. Well, think of it this way. If you have, and let's just use a whole number, 10 electrons, or 10 protons and 10 electrons. If you lose 2 electrons. Now you only have 8 electrons, but you're still held by 10 positives with 8 negatives. You're going to pull them in tighter. If, however, you still have only 10 protons, but you add 2 more electrons, you're at 12. So you're not matching 1 to 1. It's harder to keep up with them, so they tend to expand. So here, cations are smaller than the atoms they form from, whereas anions are larger than the atoms they form from. Now, I actually like this slide, form from, because what they're showing you is here is the atom, here is the ion. So all of these below the line are the atom, and above it is an ion. So notice that when you get negative, you get large, and when you're positive, you get small. And as a matter of fact, as you lose more electrons, you become smaller, because think about it, you're pulled tighter and tighter. So this to me is a really cool slide. I really like this one. This was the previous version of this text, which I thought was really cool, because remember, cations are smaller than the ions they're formed from, and these are larger from the ions they're formed from. And so here, the gray is always the atom. So you can really see the difference here. And the biggest thing is, remember the same trend, they're all going to increase straight down, whether they're positive or negative. And this is an old one that I had. It's an old Holtzlaw text, and I liked it because it put everything on there. And if you'll notice, in this area, we're avoiding the transition metals because the trends aren't as trendy. And I'll just say trends, not trendy. So we stay within the representative because they work in the S's and the P's. Okay, so that's just another example. So we're back to the isoelectronic species, and remember, isoelectronic species have the same electron configuration. And remember, the greater the nuclear charge, the smaller the species. So, for example, we saw this a minute ago. If we lose 2 protons, this will be smaller. And if you gain more, this one's actually going to be larger than this species. It should actually be put there if you're strictly doing size. So if you're looking for each of these pairs, this one asks you to choose a smaller atom or ion. If it had asked for the larger one, then you do the opposite. So we have a gold atom or a gold ion. So the smaller one will be the ion, because once you lose those electrons, you get smaller. Now, on the other hand, we've got the phosphorus atom and the P3 minus ion, which means you would gain 3 electrons. So that's going to be larger. We want the larger one. So we're going to pick the P. This one's going to be the larger. This one's going to be larger in this group. So if we're comparing 2 plus to 3 plus, the 3 plus will be smaller because it's even pulled in. So again, they're asking with these isoelectronic, and if we look at it, they're isoelectronic, so if you line it up accordingly, they're all positive, we would have cesium plus 1, barium 2 plus, and lanthanum 3 plus. So even if you didn't have the charges, they'd still be getting smaller on the lanthanum side, but with the charges, it's going to make it worse. So the largest will actually be the cesium plus, and the smallest will be the one with the minus charge. Okay, now that's that group where they're all positive, so this one is negatives. So if it were me, I'd line it up by my charge, and again, these are isoelectronic, and so we're looking for the largest to the smallest. Let's keep largest to the smallest. So again, the negatives, 2 minus is going to be greater than is 1 minus, which is going to be greater than the rubidium plus 1 charge, and the smallest will be the one that lost the most ions. Okay, and these are all the isoelectronic, and the beauty of that is we know they're connected together, so they have the exact same number of electrons. So if we look at this with ionic sizes in lithium ion batteries, this is actually cool. This is why the lithium ion batteries are better batteries in their little side notes, so you may want to read through that. The next one rule that we have is the first ionization energy. Well, ionization energy is the energy required to remove an electron from an atom in its gaseous state. Okay? So this trend basically is relatively simple. We're going to increase as we go left to right. So if you'll notice, we're going to get larger here, and we're going to decrease as you go down a family. So basically, you're going to increase up to the fluorine corner. Okay, there will be a sharp increase from the beginning of row to the next one, and representative elements have a larger range than transition. So the transition metals all seem to be comparable. So we're going to increase the ionization energy. Now remember, the ionization energy is the amount of energy it takes to rip off an electron. Well, if you remember, the metals want to lose them. They want to go positive. Nonmetals don't want to, so therefore your numbers go up. And the other thing is it's going to increase each time you remove an electron, because think about it, you pull one off, now you've got more positive, so it's not going to want to lose the second one. So that's going to go up, but it's a drastic increase if you pull from core electrons. So if we look at boron, we're losing our first electron, so we kind of like double here. And then we go up again about by, not quite by 2, and we then suddenly we can lose that first that first electron, the second electron, and the third electron. And then suddenly we're into the core here. Notice that we jump from 4,000 to 25,000. That's the difference. Let's say if you're lifting weights, you're going from 25 pounds to 2,000. I don't know about you, but I can't do that. So we're good to go on that one. So when we look at periodic table and we look at the trends, this line here are the inner shell, those are the core electrons. So these are all the valence electrons. You can get the properties associated with them. And we'll look at some of the properties later in chapter, I think, 8, but not a big deal. And using only the periodic table, arrange these atoms in order of increasing first ionization energy. Now remember, increasing is here, so if it were me, I'd set it up on my periodic table. So I have aluminum, I have argon, wait, that's in the same row, chlorine, hey look, that's convenient, sodium's in the same row, potassium's not, and silicon is right next to here. So we're going to set this up in increasing order. So if we're going to increase as we go up, increasing would be the lowest to the highest. And so we're going to start with potassium, sodium, and we're just going to follow the row across. And I'll tell you right now that noble gases will always be the highest as we go. Alright, now, one other thing we need to talk about is exceptions to the filling order. If you looked at the filling order in the book, you might have seen variations. We talked about the fact that if you have a full d orbital, you don't touch it, you don't gain or lose electrons. Well, the interesting thing about that is that you have extra stability associated if you are half full or full subshell. So, for example, if we look here, scandium is 4s2, 3d1, 3d2, 3d3, and then we jump to 3d5. Wait, we don't have any extra electrons because we had 5 electrons here, we have 4 electrons here, we have 3 electrons here, so we're going to have 6 electrons here. But what we've done is we've moved 1 from the S into the D. We moved 1 electron. Why? Because that makes the D, which holds 10, 5 is half full. And 10 is full, so we have extra stability if we're half full or full. So by popping that electron up, you'll have a half full shell. So remember when we went to copper, copper can be either 1 plus or 2 plus, and you're like, wait, but if you do the order, then it really only should be 2 plus because it's got the 2 S's. Well, again, we moved 1 from an S to a D to get a full D. Okay, so that means that you can have the 2 S's with a 3D9, or you can have 2s with a 3d10. So here you can lose 2 electrons, which gives you the copper 2 plus. Here you can lose the 1 to give you the copper 1 plus. Okay, so notice that you get these jumps when you have extra stability. So if you go back and look at the periodic table, with zinc you get a full shell, so you're only going to get a 2 plus. Same thing with cadmium. And remember we said silver, well, only was 1 plus. It's only 1 plus because what happens is it pops that S electron up to fill the D, and the D can't be adjusted, so you have to leave it alone. Okay? So it adjusts the filling order. So that allows you, because of the electron configurations and the shapes, we get the ionic charges, which we've done before, and so you're like, oh yeah, now I get that. So the other thing is with ionization energy, we lose an electron. Well, the opposite thing is electron affinity, where that's the energy change that occurs when an electron is added. So 2 things to really note: electron affinities are negative. They're negative because the process is exothermic. So you get more negative as you go over this way, and up and down there's really no trend here. Okay, but from left to right we look at it, and we're going to get more negative as we go to this end, which makes perfect sense because fluoride and oxygen and the nonmetals want to go negative. Okay, so but if you go up and down you really don't see a trend. So the other thing we need to look at is the metallic character. So basically you get more metallic down here, and here you get more non-metallic, and we're kind of leaving out the noble gases here because if you notice the metallic is going up here, the non-metallic is going up here, and let me change colors. So the metallic increase is going here. So we can look at that as we go. Now, what are the properties of metals versus non-metals? Well, metals tend to be shiny, good conductors of heat, electricity. They're malleable and ductile. Malleable means you can pound them into a flat, paper-thin thing. Ductile means you can pull them into a wire. They have high melting points and high densities. Non-metals are kind of like non-metals. If metals are shiny, non-metals are dull. Metals are good conductors. Non-metals are like, no, are not conducting anything. They're not malleable. They're very brittle. And if metals are high, non-metals are low. And the biggest thing on this one is you may be asked, a multiple choice question. Which has the higher melting point, metals or non-metals, that type of thing. Okay, again, they're showing you the oxidation numbers. Notice that in here they tend to be variable more often than not. Okay, so one other thing that we have to look at is when you mix the oxides with water, what do you get? Well, metals tend to be basic. So metal oxides tend to be basic. Okay. Non-metal oxides, so tend to be acidic. This is where you get acid rain. So SO3 plus water gives you sulfuric acid, so that's your acid rain. And then the ones on the zigzag line tend to be amphiprotic, okay? And this is amphoteric or amphiprotic. Same thing, the amphiprotic. Okay, just think, what's an amphibian? It lives half of its life on water and half of its life on land. So these tend to be the semi-metals. Okay, again, so that's trend. Now, we talked about this once before, and you'll actually see a lab coming up where you're going to look at flame colors. 4th of July is coming up, and I know with this, with some of the COVID stuff, you may not see as much, but these are really cool. This is your lithium, sodium, and potassium. So based upon the flame color, what you're doing is you're giving the electrons enough energy to be excited, and then when they fall back down, they fall down with a unique color. Okay, so we're going to summarize all the trends here. So we even threw in effective nuclear charge. Here's our increasing atomic radii, our increased ionization energy, negative electron affinity, and these basically have not much change as you go up and down for them. So we can see these properties as we go. So basically, you're just going to be asked questions about these trends. Now, the last thing is one of these chemistry and life. And as I tell you, some of them are more interesting to different people than other ones. This one's actually pretty cool because it explains how 7-Up started. And, you know, Coca-Cola was a different drug. It was the Coca drug. This one's was lithium. So they keep trying to medicate us with sodas. So be careful with what you eat. And this is really an interesting one. So we have one more section I think left in 7, and then we're done. But this is all going to be like multiple choice, fill in the blank, select, matching, that type of thing.